Hi everyone, so this is chapter 3 where we learn about electric currents and DC circuits. So to start off the chapter, I'm going to introduce you a simple circuit for now. Okay, so this is chapter 3. So chapter 3, the title is called electric current. So we're going to start off by learning about electric current. Okay, but after that, we are going to move on to study about DC circuits. DC circuits, the word DC stands for direct current. Okay, so direct current circuit means by the current is going to flow in one direction only. Okay, in our modern world, we have two types of current usually. One is called direct current, one is called alternating current. So if it's alternating current, that means the current is going back and forth in the circuit. It's keep on turning, changing direction alternatingly. But if we talk about direct current circuit, the circuit only the current only flows in one direction only. Okay, so this is the focus for chapter 3. In chapter 6 later, we'll learn about currents that flows in alternating direction. Those we call as alternating current circuits. Okay, so chapter 3, section 1, we are going to focus on the 3 important quantities that we study when we talk about electric circuits. So the 3 important quantities are, we talk about current, we talk about voltage, and we talk about resistance. Okay, it's usually, I write it usually as current, resistance, and voltage, but never mind. Okay. This is title for now. Okay, so the first thing that we're going to introduce to you, it's a basic circuit and what we can study about circuit. So a basic circuit here usually consists of a battery. Okay, that's a standard way of drawing a very basic circuit. We have battery. Then battery is connected to a resistor, usually. Okay, it can be anything. It can be a light bulb, actually. It can be a buzzer. It can, yeah, there's many kind of components you can put in, but basically something that consumes energy. Okay, so if you look at a very basic circuit, you see that there will be a battery or a power supply, a DC power supply that acts as an energy provider. Then we have a resistor or a light bulb or a buzzer that acts as a load which consumes energy. So this is the energy provider, this is energy consumer. Then how does the energy provider provide the energy to the energy consumer? It requires a pathway for the energy to be transported. So the connecting wires will play the role to transport the energy. Okay. So the 3 important elements in any kind of electric circuit, you need a battery, okay, a power supply, okay, that's right, as battery. The second thing you probably need is a resistance, or yeah, let's call it resistor. Resistor, okay, I usually call it as resistor. Okay, then the thing that I usually use is connecting wires. Okay, so if we talk about battery, the purpose is to be the energy supplier, right? So it supplies energy. Okay, whereas with the resistor, or we usually call it as load. So load is any kind of thing that consumes electrical energy. If you put in a light bulb or you put in a buzzer, or those things are called a load because they will consume energy that is being supplied by the battery. Okay, so resistor over here, it uses energy. Okay, transforming into useful work usually. If it's a light bulb, you transform it into light energy. If it's buzzer, you transform it into kinetic energy or sound energy. Okay, so it transforms into some kind of energy that is useful to work. Okay, so resistor use energy. Then next, connecting wires. The purpose of it is to transfer the energy or transport the energy. Okay, transfer energy. But how do you transfer energy? You transfer energy with the help of the charge. Okay, with the help of charge. Okay, so these are the three important elements. Let me go to another slide, which I'm going to show you important things regarding what I explained just now. Okay, so electric circuits is basically a closed loop made of conductors. So because of that, charges are able to flow along this closed conducting path. So battery inside there's conductor. Resistor also consists of some amount of conductor, so that's why charge is able to flow through it. And connecting wires, they try to be the best conductor, like copper, silver. They are the best conductor in which it can flow through easily. So basically, the whole loop here will be a conducting path. It's a closed conducting path. Means by there's no gap in between where charge cannot flow. Charge can flow completely through it. It's a closed conducting path. So charges are energy carrier. They carry electric potential energy with them, or technically they possess the electric potential energy. So because they are at high potential region, they possess greater potential energy. If they're at the low potential region, they possess less potential energy. So if they move around from high to low potential region, then they experience changes to their electric potential energy. So therefore, when the charges are flowing from one point in the electrical circuit to another point, it is essentially carrying energy to that point. So if I possess 6 joule of electric potential energy and move from A to B and there's no potential difference across A to B, then there will be no change in potential energy. So essentially what happening is before they have 6 joule, I move to another point, point B, I still have 6 joule. So that 6 joule is being transferred. Okay, so you can bring the energy from one point to another point. If there's no potential difference, then the amount of energy would not change. Then essentially you are bringing the energy to another point. Okay, so then when it passes by a certain electrical component, the charges will pass a portion or all of their energy to the electrical components that is passed through. So let's say I bring the 6 joule energy to somewhere before entering the resistor. Then once I pass through the resistor, because resistor possess some resistance, it's going to take up some energy from the charge. So therefore the charge will lose energy, the resistor will gain some energy when the charge pass through the electrical components, let's say a resistor. Okay, so the charge is moving around carrying energy. When you pass through a resistor or pass through some kind of load, then you pass the energy to the component. So the component will gain energy, then use it to do some useful work usually. Okay, so how do we make charges flow in the circuit? Okay, if you just have a piece of wire, the current won't flow. If you want to make the charges flow in the circuit, you have to create a potential difference set across the current path. Potential difference, you can think of it as height difference. Okay, so let's talk about something similar with water first, something we have discussed in chapter 2. So chapter 2 we usually talk about charges, think of it as water, right? Okay, we have charge pump, like water pump, pumping water from one plate to another plate. That is what we learned in chapter 2. Okay, so water naturally flow from higher ground to lower ground. Okay, that's what we naturally perceive. We know that water, they flow from upstream to downstream. So from up or above the hill, water flowing downhill. Okay, so making use of this knowledge, we exploit water to do work for us. This is usually in the older generation. So any kind of medieval times machine that uses water to do work usually fulfill the following two criteria. Okay, so the first criteria is a potential difference set up due to difference in height. Okay, you can see all these three water wheels over here. You can see some kind of difference in height over here. Water flowing from up from higher ground to lower ground. Water flowing from higher ground to lower ground. Water flowing from higher ground to lower ground. Okay, so the difference in height is the potential difference. So this is the high potential region. This is the low potential region. High potential region, low potential region. High potential region, low potential difference. Low potential region, sorry. This potential difference can be created naturally through river or through waterfall or multiple water catchment. Okay, so you have river, it must be flowing from somewhere high to somewhere lower. So this is a potential difference. Waterfall flow from high to low as well. Water catchment the same way. Water catchment is something like a dam. Okay, so it can also be created artificially by having a water tank set up at a high location and pump water into it for storage. this is a similar situation. So you can use some kind of device to pump water into this storage tank. So you can use it in a later time where you open up this outlet. So there will be water flowing out. So the amount of energy stored inside can be used at a later point in time when you open up this tap, letting the water to flow through it. Okay. So a path that lets water flow naturally from higher ground to lower ground while passing through device like a turbine or water wheel to harness the energy to do useful work. So if there's no water wheel over here, the water will just flow from high to low, transforming from gravitational potential energy to kinetic energy. So what happened essentially is just the water flow faster. Nothing really happened. But if you install some kind of component over here, let's say a water turbine, the water turbine will turn, right? So if the water turbine turns, it can harness the energy to do useful work. Okay, so let's say you can see there's a water turbine over here. So if you have water turning over here, you turn this gear over here, which turn a series of gear which can be used to do to make flour. Okay, so this is a video of a traditional flour mill, okay, that produce flour using potential energy of water. So water turns through the turbine, turning the turbine, which turns a series of gears to operate some machinery to produce flour. So this is how humans make use of gravitational potential energy to do work. Okay, so electric circuit actually follow a similar idea. It also follow the same two criteria. A potential difference set up due to the difference in electric potential. So you have different high potential region, you have low potential difference. So across them, you have a potential difference. This potential difference is usually created artificially by having a battery or a charge capacitor connected to the circuit. So you know that a battery pumps charges from low potential region to high potential region. So essentially you are creating that potential difference in order for charge to flow out of the battery from the high potential region to the positive terminal, flowing outside the circuit to the low potential region, which is a negative terminal. So you know that charges flow outside the battery from the positive terminal to the negative terminal. Okay, charge capacitor run on similar idea. You have a higher potential plate and you have a lower potential plate. So when you discharge capacitor, the capacitor will let charges flow from the high potential plate to the low potential plate. So high and low, there's a potential difference. Okay, a path, in this case, an electric circuit that lets the positive charge flow naturally from high potential to low potential while passing through device like the light bulb or clock to harness the energy to do useful work. So just now we talked about battery flow. You have charges flowing from positive terminal to negative terminal outside the battery. We talk about capacitor. There's charges flowing from the high potential plate to the low potential plate outside the capacitor. So if we install something on the path to flow from high to low, let's say we install a light bulb, then when the charge passes through the light bulb, okay, then you do some useful work. Let's say you light up the light bulb. Okay, so by providing a diagram, you can see that what we discussed about water pump and water flow is actually very similar to an electric circuit. So who pumps the water from lower ground to higher ground would be a water pump. So the water arrives at higher region, higher places, so it possesses greater potential energy. So when it flows naturally from high potential region to low potential region, you lose that gravitational potential energy, right? So the gravitational potential energy is actually converted into kinetic energy of this water wheel, which can be used to operate some kind of useful machinery. Same idea carries to the electric circuit. You have a battery over here which serves to pump charges from low potential region to high potential region. So when the charges go from the negative terminal to the positive terminal inside the battery, the charges will possess a great amount of electric potential energy. So we will follow through the connecting wires, but as it passes through an electric component, let's say a light bulb, then the energy, the electric potential energy will be converted to light energy to light up this light bulb, leaving the charges that pass through the electric component to have less or minimal or zero potential energy. So when it has zero potential energy, it will come back to the negative terminal, waiting to be charged again, waiting to be pumped up again to a higher potential region, and the cycle just follows. Okay, so in that case, we can analogize the battery as a pump that brings the positive charge from region of low potential, the negative terminal, the region of high electric potential, the positive terminal. Okay, so the positive charges then leave the battery from the positive terminal, traveling through the connecting wires with minimal potential difference. That means from here, say this is a battery, right? It pump that it has high energy. This journey from here to here, actually there's no energy loss. Okay, we assume that this is an ideal connecting wire, so you not consume any energy at all. So if you have 1.5 joule energy over here, that 1.5 joule energy will continue until this point. Only when it passes through a light bulb, that 1.5 joule energy will be lost, will be given to the light bulb to light up. Then you leave us with 0 energy, bringing us back to the negative terminal. Okay, so connecting wires not supposed to consume any energy, idealistically, but when it passes through any electrical component, then it might take up the energy from the charges. Okay, so it travels through the connecting wires with minimal potential difference, therefore there's no energy loss before passing through any load. So the load over here is a light bulb, while dropping through a significant potential drop. So just now it's a potential gain, right now it's a potential drop. So when it's a potential drop, the charge will lose energy. Traveling through a potential drop, causing the positive charge to lose their potential energy to the load. So the load receives the amount of energy and it can be transformed into useful work. So work done is equal to Q delta V in chapter 1. Okay, so when I say 1.5 joule, it means that 1 coulomb of charge passes through this battery. This battery 1.5 volt, that's why this 1 coulomb of charge passing through the battery will gain 1.5 joule of energy. So if the voltage across this light bulb is 1.5 volt, that means when the 1 coulomb of charge passes through the battery, you do 1.5 joule of work done. So that 1.5 joule of work done is the light bulb lighting up. Okay, so it will come back with 0 joule energy to the negative terminal. Okay, so this is a rough idea of how you should think of a circuit. Think of it as if it's similar to a water pump, water flow, and water turbine kind of analogy. Okay, so next we are going to continue with the notes again, where we're going to talk about current for now. Okay. So in this part of the notes, I'm going to talk about current. Okay, so to talk about current, let me define some of the important things first. Okay, so current, the symbol is I, and the unit is ampere. A. Okay, so right now I'm not going to go through the mathematical stuff first. What I want to discuss with you right now is how do we have current flowing in the circuit in the first place. So to talk about how current flow through the connecting wires in this kind of closed circuit, we are going to bring out the microscopic model of current to discuss this how current flow kind of question. Okay, so what I have here today is we have a battery with a connecting wires connecting it to the resistor. So the resistor have some kind of resistance bands. You have red, yellow, brown maybe, and gold, let's say. Okay, so this is resistor. So this plays a role as energy supplier. This battery, this resistor plays a role as energy consumer. Then you have connecting wires to allow the current to flow through the battery and also the resistor. Okay, so what happens is when you have this battery installed, what will happen is we know that the battery consists of a high potential terminal and a low potential terminal. So we know that the positive terminal over here is the V high, whereas this low potential terminal is the V low, right? So essentially what happens over here is this battery sets up a potential difference with a high potential region and a low potential region. Okay, so I want you to recall a little bit from chapter 1. Chapter 1, we learned that if it happens to have a capacitor, okay, this is just a rough drawing. If it happens to have a capacitor, so a capacitor usually, once it's charged up, there will be a positive plate. There'll be a negative plate, right? So we usually call the positive plate to be V high, the high potential plate, whereas the negative terminal will be the negative plate will be the low potential plate. And we know that in between the high potential plate and the low potential plate, there will be uniform electric field pointing from the high potential region to the low potential region. This is what we learned from chapter 1, and it connects to chapter 2 as well when we talk about parallel plate capacitors. Okay, so this is what we know from last time when we talk about electric current. There's uniform. When we talk about capacitor or talk about two parallel plates, there will be electric field pointing from the high potential region to the low potential region. So carrying that story into this current circuit over here, we know that this is V high, this is V low, right? So if you're observing the connecting wires, what will happen in the connecting wires is there will be an electric field that is pointing from the high potential region to the low potential region. So we should expect some kind of electric field going in this clockwise direction from the high potential region to the low potential region outside the battery. So this is what we should assume. Then we can label the direction of this electric field to be pointing from the high potential region to the low potential region. Okay, even inside the resistor, the similar things also happen. Okay, so I'm going to label this as the electric field. Okay, so this is what happens when you have battery. You connect the battery have V high, V low. The electric field will point from the high potential region to the low potential region. Okay, so now if you want to focus on what is happening inside the wire, we know that wires are made of metal, so we want it to be a conductor, right? So good conductors are like copper or like silver. These are good conductors. Okay, so if you want to observe inside this kind of conductor, you might need to employ something we learned from chemistry, which is the electron C model. Okay, so now let's forget about the battery first. Let's think about what happens in the connecting wire, in the structure inside the connecting wire when there's no battery connected to it. Right now, this is without battery. Okay, so without battery, I would like you to try to take something from chemistry, which is the electron C model. Think about this situation over here. So when we learned about electron C model in chemistry, what we learned about is that there will be these kind of ions. There's valence electrons to it, right? So these valence electrons will delocalize from the electrons, from the atoms itself. So you come out from the atoms, these valence electrons, and they are able to freely float around the metal, inside the metal. Okay, so what we have over here when I draw this, these are the atoms actually. These are the metal atoms actually. But what happened to these metal atoms is that their valence electrons has already delocalized from the metallic atoms. So when you have electrons coming out from this atom, so there's a loss of negative charge, right? So the loss of negative charge means that there's more protons compared to electrons. So what happens here is these metallic atoms has already turned into ions. Okay, so what we have in these red circles over here, these are positive metal ions. Okay, so metal ions come from metallic atoms which have their valence electrons delocalized from the region already. Okay, so you have electrons floating around right now. Okay, so these electrons are floating around, and based on electron C model, we know that they are not really bound by the metal ions anymore. So when they're not bound by the metal ions, they're able to freely float around the region, moving around. Okay, it's not bounded by the metallic ions anymore. Okay, so when we say they are able to freely move around, that means the kind of motion that we should be seeing for the electron should be some kind of random motion. But we know that electrons actually move very fast actually. So we should expect the motion of the electron to be fast, random motion. Okay, the kind of motion we can observe for the electrons should be fast, random motion of electrons. Okay, so if there's no if there's no positive ions that is available in these connecting wires, let's say there's no positive ion at all. So if it's moving fast and random, you eventually get faster and faster because there's no one blocking them. But what happened is now you have these positive ions over here. Actually, they don't really move faster and faster. They just move around, just like gas particles in a gas container. They just move fast and random. Okay, for now. Okay, even though you remove all these positive ions, they will still move fast and random, just like gas particles in a gas container. But we know that there's a lot of positive ion in these connecting wires. So these positive ions, they won't move, right? They are fixed in a certain metallic structure. Okay, depending on what kind of metals you have different kind of lattice structure, I think. Okay, but solid, you know that their atoms are closely arranged and they have a orderly arrangement, right? Okay, so these positive ions are well arranged in a fixed kind of structure, so they will not move. So what happens is when the electrons, they float around in this region, we should expect that they will be bouncing around this region over here, bouncing, colliding with all these positive ions and not container, but just bouncing around these positive ions. Okay, so what we should expect is, besides having fast random motion of electrons, there will also be frequent collisions with the positive ions. Okay, so sometimes you might be moving to the right. These electrons might be moving to the right, but as it hits onto a positive ion, it might change direction to be a left. So there's a lot of up, down, left, right happening. So essentially the charge is not going anywhere. It's just bouncing around, sometimes to the left, sometimes to the right, sometimes upwards, sometimes downwards, sometimes to the front, sometimes to the back. But essentially there's no particular direction in which all the charges, all the electrons are moving. So all the electrons are just bouncing around randomly. Okay, so what we can say is, if we combine the fast random motion of electrons together with the frequent collisions with positive ions, well, what happened is nothing happened really. There's no drift around, there's no drift to the electrons. You don't see it particularly move to the left, you don't see it move particularly to the right. It just bounced around its own place. Okay, so to help you illustrate the idea, let's probably focus on one single electron and see how it will bounce around. Okay, so let's say this is the electron that I'm going to observe, then the path might be something like this. Okay, you can see it bounce to, now it seems like it's moving to the right, but as you can see, at a certain point, oops, now it's bouncing towards the left. It might go even more left. Okay, I'm just randomly scribbling around. Just to let you know that there's no particular sense of direction. You can see sometimes occasionally it's moving to the left, sometimes occasionally it's moving to the right. But because there's the same amount of left, there's the same amount of right, there's the same amount of up, down, left, front, back, because it's moving randomly, right? Any direction is possible. So that collision will cause it to actually go around in its own place only. You won't see the electron slowly going towards the right, slowly going towards the left. No such thing happen because there's no guided direction. Okay, there's no guidance at this moment. Okay, but things become different when you insert a battery to this circuit over here. Okay, as we mentioned just now, this battery over here will introduce a potential difference and it will cause a uniform electric field to be pointing from the high potential region to the low potential region, right? So you should expect now there will be an electric field that we have to this connecting wires or this metal right now. So let me label this as the electric field. Okay, so this is a situation where we have battery right now. Okay, so right now things is not that simple anymore. You still have fast random motion. The electrons still move very fast. That is still true. So fast random motion of electrons. And you still have frequent collisions, that those things are still there. Okay, the electrons still move in a similar kind of behavior. Okay, well, what happened right now is, because this is an electron and electron is a negative charge, and right now there's electric field in the region, right? So this is your electron. The electron is a negative charge, so you interact with the electric field that we see in the connecting wires right now. So in the connecting wires right now, we have electric field pointing to the left. So let me draw this as E. This is the electric field of the electron pointing to the left. So right now, because you're interacting with this electric field over here, what happens is this electron will experience a force as a result of the interaction. So the direction of the force, because this is electron here is a negative charge, the force experienced by this electric charge, which is negative here, will be opposite to the direction of the electric field. You need to review chapter 1 to understand this. If it's a negative charge, the force and the electric field should be in opposite direction. That's why you should expect that the electron over here will be experiencing a force pointing to the right. Okay, so with this Coulomb force added to the mix, okay, this is a Coulomb force. What happened right now is, even though it's moving in the random kind of direction, but there's some kind of guidance to it. Okay, it's as if you are asking this electron to bounce around. You're asking this electron to bounce around, but you are blowing a fan from the left hand side. You're blowing a very strong fan from the left hand side, blowing it towards the right. So even though the electrons are moving randomly, but because there's some kind of guidance to it, this electron will slowly actually drift to the right. Okay, you can think of it as putting a fan over here to exert a large force towards it. So even though the motion that it behaves is a random kind of motion, but there's a constant force pushing it to the right. That's why you can see this electron eventually will drift to the right. Okay, so let me draw how it moves. Okay, the kind of motion that you observe will still probably be a random kind of motion, but any chance that you have to move to the right, you actually move more. Any chance that you have to move to the left, actually you move a bit less to the left, because there's great resistance to move to the left. So essentially you can see that the electron is actually drifting to the right. Okay, so even though the electron is moving very fast, okay, but there's a lot of collisions with the positive ions. So it cannot just keep accelerating to the right, then it eventually moves super fast in the circuit. That is not how electron works. There's too many positive ions for it to collide. So there's too many change of direction, bouncing around. So even though the electrons are moving very fast, right? But because of all the bouncing around, the motion to the right actually is very slow. Okay, because this positive ions collision always cause it to change direction. So eventually your electron can't really drift to the right that fast. The drifting of the electron to the right is actually quite slow. So even though the motion of the electron is fast, but the electron only move gradually to the right because of all these collisions that we have here. Okay, so we can come to a conclusion that combining all three factors that we see over here, what we observe is the electrons will drift. But the kind of drift that happens is a slow drift. Okay, electron will drift slowly in the direction opposite to the electric field. Okay, so you can see that the force is pointing to the right, therefore you can see the drift is to the right. Okay, so to the right means that it's opposite the direction of the electric field. Okay, so this thing here tells us how the electrons will move in the circuit. So if electrons are moving very fast in the connecting wires, but if you want to observe how electrons move from the high potential region, from the low potential region, how it move to the high potential region, in this direction, right, the electrons move. The kind of motion that you see for the electron is actually very slow. The drift of the electron from the low to the high region is very slow, even though the electron itself is moving very fast. Okay, so this is the idea that I want to carry, and this whole thing here is called a microscopic model of current. Okay, so to illustrate the idea better, I'm going to show you some slides that I've made. Okay, so just now we talk about electron C model, right? Oops. So you can see that these positive ions, they are all arranged in a fixed kind of lattice. But right now you can see that the electrons are sort of randomly just moving around in between all these positive ions. We call this delocalized electrons, right? They are just moving around in random motion right now. Okay, so the free electrons move randomly in the conductor while colliding frequently with the positively charged ion. So the electrons, they are actually moving very fast. They are moving at about 1% of the speed of light. Okay, so you can see if it starts here, you bounce, 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 bounce. But essentially, you can see that after some time, it actually just moves around in its own place. You can see that after all the bounce around, moving, whizzing around this, in between the electron ion, in between the positive ion very fast, all this whizzing at the end bring you back to similar places. Okay, so you can see that there's no particular direction that the electron is heading towards. Okay, but right now, things will be different if a potential difference is introduced across the conductor. So right now you have a high potential over here because this place is connected to the positive terminal. You have a low potential because this place is connected to the negative terminal. Actually, this picture over here is the opposite of what I drew just now. Just now I draw the high potential to be here. I draw the low potential to be here. But this is just another example where this is high potential, this is low potential, because you connect it to the positive terminal of the battery. For this side, you connect to the negative terminal of the battery for this side. Okay, so what happens is, first you have a uniform electric field produced across the wire. So it goes from the high potential region to the low potential region. That's why you can see this electric field is pointing to the right now. Okay, so when you have electric field pointing to the right, the electrons will experience an electric force. Why does it experience an electric force? Okay, it's because it interacts with this electric field over here. The electric field is pointing to the right, so the electric force will be pointing to the left because electrons are negatively charged. So the force experienced by the charge is opposite to the direction of electric field. So all these electrons are experiencing a force to the left. So this force to the left will actually causes an acceleration opposite to the direction of electric field. So we know that sum of F is equal to ma. So if this is the force experienced by the electron, so the acceleration will be pointing to the left as well. Okay, so if the electron is moving in vacuum where there's no positively charged ion, just imagine you erase off these positively ions, this steady force will cause a steady acceleration because this force is constant because it's a uniform electric field. So E is constant, F is constant, so A will be constant, there will be a steady acceleration. Then you will see this electron just gradually speed up, 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 never really slow down, if there's no positive ions in this conductor. But in reality, there's positive ions in the conductor, right? So there will be frequent collisions with the massive near stationary ions of the material. All these positive ions, they are technically not moving, so you're really colliding with them. But because these positive ions are very big, they will not budge. So what happens is only the electron will change direction. The positive ion will just stay there. So you'll be bouncing around, bouncing around, bouncing around, bouncing around. So there's a random change of direction to the electrons due to all these collisions with the positive ions. Okay, so what happens is you have electrons experiencing a force, but you also have electrons moving in random motion due to the collisions with nearly stationary ions. So what happens is the usual cases you have a lot of bouncing around. Essentially, you're just moving around the same region, whizzing around. But right now, the electrons are moving with a very fast average speed of 9 times 10 to the power 6 meter per second. But due to this electric force that we mentioned just now, there will be a slow drift towards the direction of the force. So initially, if it's moving like the light gray kind of that direction right now, what happens is due to the force, it experiences some kind of acceleration that directs it slightly to the left. Okay, so even though it starts and ends in similar places initially, but due to that electric field, due to the electric force, due to the acceleration, you can see that after all that bouncing around, there's actually some amount of drift in the direction of the force, or opposite the direction of electric field. There's some of drift after you let it whisk around for some time. Okay, so the velocity Vd, which we call it as drift velocity of the electron drifting in the direction of the electric force, is very slow. All this whizzing around is very fast, but the net effect of it is actually just a very slow drift in the opposite direction to the electric field. This motion here, this red color velocity here is very, very slow, but this black arrow over here is very, very fast actually. Okay, so this whole explanation here is called a microscopic model of current. So instead of really explaining all this kind of frequent collision, random motion, whizzing around, causing a slow drift, we can actually simplify the diagram over here to be something like this. So when we simplify it that way, we remove all the positive ions in the diagram. We just focus on the electron drifting. But if we are talking about the absence of this positive ion, we cannot talk about all the bouncing around anymore, right? So if we don't want to talk about all the bouncing around, we can just simplify it to say, oh, electrons, they are actually drifting slowly in the connecting wires. They are all just moving slowly in the direction opposite the opposite the uniform electric field. They're just drifting slowly, but in reality, it's not that way. They're actually moving very fast, but there's a lot of bouncing around. But to simplify the situation, we just talk about it as if it's actually drifting slowly opposite the direction of the electric field. Okay, so we can represent the electrons flowing in the conductor using this simplified model where the electrons are drifting with drift velocity of Vd. So all these electrons here, they are moving slowly in the opposite direction of the uniform electric field. The velocity of it is called the drift velocity. This is not the actual thing that happened, but this is a simplified way of explaining the circuit. Okay, so this thing, I probably won't use this slide maybe, but you can certainly talk about it. Okay, imagine, but this is not true. Imagine today what you learn in chemistry is called a positively charged ion C model. So let's say today chemistry is just different. What is fixed is the electron. The electron cannot move. Then what happens is right now there'll be positive ion, delocalized positive ion. Let's say the chemistry in this world is different. It's a positive that is delocalized, they are able to freely move. So if you go through the same explanation, you see that it will move in the same direction of the electric field, because positive charge E and F are in the same direction. So if this is a new world where electrons are fixed but positive ions are freely moving, you end up with the explanation where the positive ions are drifting in the same direction as the electric field. So you can see positive charges are drifting with Vd, but in the opposite direction of the electron. Just now the electrons are moving to the left, but right now the positive ions are moving to the right. So they're going from the positive terminal of the battery to the negative terminal of the battery. Well, this is what we usually think of actually. We have current flowing from positive to negative outside the battery, right? So this is the way we usually think about a current actually. Okay, so this is a long one. You have to follow me for it. So from the imagination process just now, we see that if we don't know either electron or positively charged are moving or stationary, we can interpret the situation in either of the ways below. Let's say we are not able to study what's happening in the connecting wires. So there's two possible versions of things. One is the delocalized thing is the electron. One is the delocalized thing is the positive ion. We don't know which one is moving initially. Back then, when we discover current, we still don't know about who is moving. We still don't know there's electrons or protons or neutrons. Those kind of things come later actually. We learn about current, we use current well before we know that there's protons, electrons, and neutrons, all these things inside. Okay, we just know that there's charges flowing, but we don't know whether the charges is positively charged thing flowing or negatively charged flowing. That's history. We don't know all those things at that time. Okay, so to explain the whole situation, we can think of two possible versions of things. One is the negative charge that is actually moving. So that negative charge will be drifting along the conductor from low potential to high potential region. Okay, this is one version of things, how we explain it, where we have electron moving from low to high. Why low to high? We can see the whole explanation already. This is high, this is low, but you can see that the electron experience force pushing it from low to high. This is if the electron is moving kind of version. Okay, the second version is the positively charged ion that is moving, but it is moving from high potential region to low potential region. So this is this version where you have a positive ion moving from high potential, the positive terminal, to low potential, the negative terminal. So there's two possible versions of things actually, because at that time we don't know who is moving. Okay, but we know that as human, right, we are naturally comfortable with things moving from high potential region to low potential region. High potential region is places which are higher. Low potential region are places which is lower. High gravitational potential, low gravitational potential. That objects naturally fall from higher ground to lower ground due to gravity. That's just how we perceive things in the world. We usually are comfortable with things naturally falling. We don't really see things happening floating up to higher ground naturally. Okay, therefore we conveniently choose to interpret the electric circuit using the second way. It's easier for us to understand electric circuit if the charge that is moving is a positive charge. Okay, it will be easier to understand the flow of current if it's a positive charge flowing, because that way the charge will be flowing from higher potential region, which is positive terminal, to lower potential region. High to low moving naturally is something that we are used to. Moving from low to high naturally is not something we are used to. That's why if the world behave as if the positive ions are moving, it will actually be simpler for us to understand the circuit. But as science progressed, we discovered that it's the electrons, not the positive charge, that are moving in the conductor. Just sadly, we bet on the wrong charge to move. We initially bet that it was the positive charge that moving, but sadly not. It's not. Okay, it's the electrons that is moving. So it's just we make a wrong decision. We bet on the wrong thing. So it's the electrons that are moving, but it's too late to really change the convention. Our science has progressed a lot from that point onwards. We already used to think of it as positive charge flowing already. Okay, but if you think about it, there's no big harm about it. Okay, because you can just think of it's the opposite of electron that is moving imaginarily. The whole thing still work. Okay, so when we talk about there's no big harm though, since we don't really care what charge is moving. We just want it to work, right? So we don't really want to focus on what charge is actually moving. So when we talk about current, we still continue to talk about flow of positive charge. We won't really focus on the flow of electrons. Okay, the reality, yes, it is the flow of electron that is moving, but to make our understanding easier, we will just think about it as if it's positive charge that is moving inside, even though it's not. But it's just simpler to understanding that way. Okay, if we talk about positive charge. Okay, so this is a long-winded explanation, but I hope you can see the history of science, how it progressed, and that is actually an interesting thing. It's like the scientific community are betting on the positive charge to be moving, but at the end it's the negative charge that's moving, but the bet is just too heavy. We cannot just change so many things. There's so many things to be changed, so we just say let's just keep it as if it's the positive charge that's moving. Then that way all the signs can remain the same. There's no need to change a lot of things. We just need to know that actually the things that's moving is the electrons. Okay, so I'm going to continue and fill up the notes over here. Wow, this is a long video, man. Okay, so what I'm going to do is I'm going to say even though this is the actual thing that is moving, but we are going to simplify the situation. We are going to simplify the situation as if right now the situation is there's electrons just slowly drifting. We don't want to talk about the positive ions anymore. We are just focusing on the electrons moving. Okay, so the motion of it will be to the right with the velocity called as the drift velocity. So we can imagine as if electrons are moving unobstructed, but the motion of the electron is very slow. Okay, this is imagination. The thing that actually happens is not this. So we just think of it as if it's drifting slowly in the opposite direction of the uniform electric field. Okay, but as I mentioned just now, this one, it's not so intuitive to understand. Okay, not so intuitive to understand. Why is it not so intuitive to understand? Because it naturally moves from low to high. Okay, low to high natural motion is not something we are used to. We are used to things falling from higher ground to lower ground. We are not really used to things naturally moving from low to high. If you see this electron, if it's moving to the right is this direction. Moving to the right, it bring you from low potential region to high potential region. So low to high naturally moving is not something it's not something easy for us to understand. Okay, so this is difficult to understand. So the scientific community choose to be a bit ignorant at this moment. I just say, let's just make it as if it's the positive charge that's moving. Because if it's the positive charge that is moving, it's easier to understand. So right now we change it into another version, okay, where it's the imaginary positive charge that is opposite to the electrons. Okay, these are imaginary charges, but they behave opposite to an electron. So because they behave opposite to an electron, they'll be moving in the opposite direction. Okay, this time it's moving in the same direction as the uniform electric field. Okay, so if it's moving that way, then it's more intuitive to understand right now. Why is it more intuitive to understand right now? Because right now you can see that the charges are naturally moving, but they move in the direction from high to low. Okay, so this is easier to understand. So the scientific community choose to think of conventional current as positive charges that is moving. Okay, so this is what we call as the conventional current. Okay, it's just easier to understand if the charge that is flowing is actually a positive charge. Okay, so that concludes what I want to discuss regarding the microscopic model of current. Hope you have a clear understanding of it. So that's it. Now I'm going to move on to the mathematics. I'm going to move on to the mathematics of the current right now. Okay, let me clear up this spot over here. Oops. Just want to clear this out because I need this space. Okay, now let's go. Okay, so right now is okay, so right now we are going to talk about current formally in terms of mathematics. So current, I believe all of you are aware about this. Current is a rate of flow of charge. So it means by how fast are the charge flowing through the conductor. So because we are talking about how fast is a charge moving, so you definitely know that current I, we have to divide by time. Okay, so because you're talking about rate, right? So you have to differentiate against time. So what are we measuring against time? We are measuring how much charge is flowing against time, right? So therefore up here you need to have charge. So this is the equation dq dt. That is important. But of course, if you are substituting, you cannot substitute up down with a differentiation, right? So usually when we want to substitute charge as the numerator, time duration as the denominator, we usually change the equation to be q over t first. That way we are able to substitute the numerator and the denominator separately. Okay, so we should know that all these electrons or all these positive charges, when they are moving, right, each electron doesn't represent 1 coulomb. This is not 1 coulomb, 2 coulomb, 3 coulomb, 4 coulomb. It doesn't work like that. We know that electrons, the charge of an electron is negative 1.60 times 10 to the power of negative 19. And the imaginary positive charge is the opposite of an electron, right? So opposite of electron means by these charges are actually positive 1.60 times 10 to the power of negative 19 coulomb. Okay, so how are you going to know how much charges are flowing through this conductor? So what I can do is I can set up some kind of like a place to do my measurement. Then I can see how many charges are passing through. 1, 2, 3, 4. Let's say 4 charges pass through in 1 second. So in 1 second, I see 4 charges pass through. Of course, I cannot see, but the idea is like this. Okay, there's 4 charges passing through. Each charges are holding or possessing the charge of 1.60 times 10 to the power negative 19. So if I want to know how much charge has flown through, what I need to do is just taking the number of charge that has passed through, multiply by the charge possessed by each charged particle. Okay, maybe there's a lot of charge in the sentence. Let me repeat again. What we want to do if we want to determine how much charge pass through is to measure how many charged particles pass through this point in 1 second. Let's say I set a barrier over here, not barrier but some kind of checkpoint. Then I see how many charged particles pass through this checkpoint. Then I multiply by the charge possessed by each charged particle. So that will allow me to know how much charge has already passed through this checkpoint. Okay, so that leads us to another equation, which is Q is actually equals to NE. So that means by you count how many charged particles has passed through the checkpoint, how many charged particles pass through, you multiply by E. E is the elementary charge, which is the charge possessed by every single charged particle. So if you multiply the number of particles, multiply by the charge possessed by each particle, you're able to know the total charge that has passed through within that duration. Okay, so that allows us to manipulate the equation further. Right now you can substitute the NE to replace the Q. Because you know that E, its elementary charge, is a constant value, you can bring it out of the differentiation bracket. So now you've arrived at another equation where E is outside the differentiation bracket and you have dN dt, which is the number of charged particles that flows through per second, or the rate of flow of charged particles. Okay, dN dt is rate of flow of charged particles. I, current, is the rate of flow of charge. There's no particles to it. Okay, so this equation is also very important as well. So usually we'll be switching around this equation and this equation with the help of Q is equals to NE when we are solving any kind of questions regarding current. So all those things that are squared up are actually important. Okay, so many students will get confused with all these symbols. So let's maybe take some time to write down all this important information. Okay, I here is current. Okay, what is Q? What is N? And what is E? Is that everything that I want to discuss? I, Q, N, E. Okay. Oh, there's one more thing, dN dt. Oops. I don't think there's a need to discuss about Q. So I, dn dt, n, and E. Okay, I is current. Current, another name of it is the rate of flow of charge. Okay, but dn dt here is not current, but it's the rate of flow of something. But right now, because n is the number of charged particles, right? So this is actually rate of flow also, but it's the rate of flow of charged particles. Okay, the particles behind is important because that means that we are counting the particles, we are not calculating how much charge they pass through. Rate of flow of charged particles, but you can sometimes call it as electrons because it's the electrons that is moving, right? Okay, so these two things you need to differentiate between them. If you want to talk about the unit for current, you can see that it's actually taking charge divided by time, right? So it's actually coulomb per second, but you can sometimes just call it as ampere. Okay, dn dt over here is not calculated based on charge, it's based on charged particle. So charged particle, there's no measuring unit to it, so we can just call it as per second. Okay, continuing from there, we have n and E. N is just number of charged particles or number of electrons. Okay, and lastly, you have E over here. This E over here is called elementary charge, means by each charge, each basic charge, for instance, electrons and protons, how much is their magnitude of charge? Elementary means basic, right? So basic charge that you have is electron and protons. So what's the amount of charge for electrons and protons? It's called the elementary charge. Okay, so elementary charge is actually a standard constant number. Okay, and the number is what I've written just now. Elementary charge, the value is just 1.60 times 10 to the power of negative 19 coulomb. Okay, so these are the important values that you need to understand the difference between them in order to solve questions regarding current properly. Okay, so that wraps up my discussion on current. We first went through an introduction of what's happening inside a basic circuit, who supply energy, who use energy, who transport the energy. Then we talk about the microscopic model of current and how we simplify things using the idea of drift velocity. Okay, so we talk about why we need to switch it to positive charge because it's easier to understand, and that forms our understanding of conventional current. And lastly, we talk about the mathematics of current, where we learn about it as the rate of flow of charge, which can be further manipulated to be depending on the rate of flow of charged particles. Okay, so in the next video, I'm going to move on to talk about resistance and the factors affecting resistance, which leads towards Ohm's law and power and energy further down the road. That's it for this video. Thank you very much.